Hello my dear friends, welcome to all of you. Myself Dattu Patel, Assistant Professor from LJIT. Today's session we are going to discuss about our new unit, which is higher order ordinary differential equation. Let's see. Firstly, we have to discuss about the homogeneous linear ordinary differential equation of higher order with constant coefficient. See, these are the outlines which is learned in this particular unit. Firstly, linear differential equation has basically two types, homogeneous and non-homogeneous differential equation. Then after we discuss about the Euler's-Cauchy equations, then after we discuss about the Li and Ld, that means linearly dependence and linearly independence of a solution. Then after we discuss about the method of variation parameters. Then after we discuss about method of undetermined coefficient. Let's see. Firstly, what is higher order linear differential equation? Then higher order linear differential equation is in form of a0 d raised to n y by dx raised to n plus a1 d raised to n minus 1 of y upon dx raised to n minus 1 plus and so plus a n y equal to r of x, where r of x is a function of x and a0, a1, a2, a3 up to an are arbitrary constant. See, here our differential equation which is in terms of y dash, y double dash, y triple dash and so on. If our differential equation which is in terms of y dash, then we can say that it is first order differential equation. If it is in terms of y double dash, means that is second order differential equation, and more than second order, second or more than second order, then we can say that it is higher order linear ordinary differential equation. Here this differential equation can be written in form of operator. See, capital D which is indicated by the d by dx, where d indicated by the differential operator which is obeys the law of algebra. See, then here we can written as a0 d raised to ny plus a1 d raised to n minus 1 y plus n so plus an of y equal to r of x. In this equation, y which is common out, that will give you a0 d raised to n plus a1 d raised to n minus 1 plus n so plus an of y equal to r of x. This term indicated by the f of d of y equal to r of x. Let's see. Next one is a homogeneous linear ordinary differential equations of higher order with constant coefficient. An ordinary differential equation which is in form of a0 dny of dx raised to n plus a1 dn minus 1 of y upon dx raised to n minus 1 plus and so plus n of y equal to 0. See, is equal to 0, then we can say that it is homogeneous. Is equal to something value in function of x, like as x, cos x, sin x, x square, etc. Then we can say that it is non-homogeneous ordinary differential equation, where a0, a1, a2, a3 and so on are arbitrary constant, is known as homogeneous linear ordinary differential equations of order n with constant coefficient. This equation is known as linear since the degree of the dependent variable y and all its differential coefficient is 1. Let's see general solution of homogeneous linear ordinary differential equations. See, whenever we finding the general solution of homogeneous ordinary differential equation, we have the basically four cases. Case 1, when all the n roots of the auxiliary equations are real and distinct, that means values are non-repeated. Here m1, m2, m3, m4 and so on up to mn be a real roots of the auxiliary equation, but condition is m1 which is not equal to m2, which is not equal to m3 and so on up to not equal to mn. That means e raised to m1x, e raised to m2x, e raised to m3x and so on up to e raised to mnx from the linearly independent solution of the differential equation. Then our general solution, which is y of x equal to c1 e raised to m1x plus c2 e raised to m2x plus c3 e raised to m3x and so on plus cn e raised to mnx, where c1, c2, c3, c4 and so on are arbitrary constant. See one example, m equal to 1, 2, 3. Suppose our factors 1, 2, 3, otherwise minus 1, minus 2, minus 3, etc. Then our general solution becomes y of x equal to c1 e raised to x plus c2 e raised to 2x plus c3 e raised to 3x. Let's see one example based on the case 1, 2d square y plus dy minus 6y equal to 0. Here our question which is in form of operator form. Maybe sometimes our question which is in form of ordinary differential equation, likewise that y double dash means 2y double dash plus y dash minus 6 equal to 0. In university exam maybe ask our question in this form. Then firstly what we have to do, rewrite the equations, then we can written in terms of operator. Then 2d square y plus d y minus 6y is equal to 0, where capital D equal to d by dx, that is our differential operator. Now 2d square plus d minus 6 of y equal to 0. Now our auxiliary equation is, then it becomes 2m square plus m minus 6 equal to 0. Now factorize 6 to the 12, then factorize this term, then 4 3s are, then 2m square plus 4m minus 3m minus 6 equal to 0. Then in first and second term 2m which is common out, then it becomes m plus 2. Second and third and fourth term minus 3 which is common out, then it becomes m plus 2 equal to 0. Then our factor becomes m plus 2 m minus 3, sorry 2m minus 3 equal to 0. Then compare with 0, then m plus 2 equal to 0 and 2m minus 3 equal to 0. Then m equal to 3 by 2 and m equal to minus 2. Here our factors are minus 2 and 3 by 2, which is real and distinct. Means we use the case 1. Then our general solution is, here we use the case 1. Then general solution is y of x equal to c1 e raised to m1 x. Then here e raised to minus 2x plus c2 e raised to 3 by 2x. That is our answer. This one is our general solution, where c1 and c2 are arbitrary constant. Let's see the case 2. When all the n roots of the auxiliary equations are real and equal, that means repeated. Let m1, m2, m3 up to mn be a real roots of the auxiliary equation. That means m1 equal to m2 equal to m3 and so on equal to mn is equal to m, means each and every factors has same value. Then e raised to mx from the linearly independent solution of the given differential equation. Then general solution of the case 2, which is y of x equal to c1 plus c2x plus c3x square plus c4x cube and so on plus cn x raised to n minus 1 e raised to mx, where c1, c2, c3, c4 and so on are arbitrary constant. For example, suppose our factors are minus 1, minus 1, minus 1. Then here values are repeated 3 times, that our arbitrary constant are up to 3, means c1, c2, c3. Then our general solution is y of x equal to c1 plus c2x plus c3x square into e raised to minus x. Let's see one more example. d square y plus 4dy plus 4y equal to 0, where y of 0 equal to 1, y dash 0 equal to 1. This is indicated by the IVP. IVP means initial value problem. With the help of IVP, we can find the particular solution. Let's see. First, we finding the general solution. Then after we go for the particular solution. First, rewrite the equations. Then here, we can written as a d square plus 4d plus 4y, which is common out, equal to 0. Then our auxiliary equation is m square plus 4m plus 4 equal to 0. Now factorize that term. Then this auxiliary equation which is in form of a square plus 2ab plus b square, then it becomes m plus 2 whole square equal to 0. Then whenever we factorize this term, then it gives m equal to minus 2 minus 2. Means here roots are real and repeated. Means we use case 2. Now general solution is y of x equal to c1 plus c2 of x e raised to mx. Then here minus 2x, this one is our equation number A. Now here our question, this one is our general solution, but our question has a something value, that is IVP, initial value problem. Y of 0 equal to 1 and y dash of 0 equal to again 1. Now just we finding the particular solution with the help of IVP. For that what we have to do, obviously here we require the y dash, then differentiating equation number A, differentiating equation number A, then y dash of x equal to, here we apply the product rule, u as it is, derivative of v means e raised to minus 2x into minus 2 plus e raised to minus 2x as it is, derivative of u, derivative of c1 that is 0, here c2, that means minus twice e raised to minus 2x c1 plus c2x plus e raised to minus 2x into c2, that is our equation number B. Now what we have to do, with the help of IVP we substituting this value, means our IVP which is y of 0 equal to 1, means that is the values of x, that is the values of y. Now x equal to 0 and y equal to 1, substituting in equation number 1, then our equation number 1, that is y of x equal to c1 plus c2x e raised to minus 2x. In this equation substituting the values of x as a 0 and y as a 1, then 1 equal to c1 plus c2 into x, that is 0 e raised to 0, means c1 is equal to 1, that is the values of c1. Similarly we have the another IVP, y dash of 0 equal to 1, means that is the values of x, that is the values of y dash, then x dash equal to 0 and y dash equal to 1, substitute in equation number 2, which is y dash of x, which is y dash of x equal to minus 2 e raised to minus 2x inside the bracket c1 plus c2x plus e raised to minus 2x into c2. Then here this one is a 1 equal to minus twice e raised to 0 c1 plus c2x, that is 0 plus c2 kept as it is, understood, into e raised to 0. And values of e raised to 0, that is 1. Here values of c1, this one is minus 2, values of c1, that is 1 plus c2 kept as it is, then 1. Then c2 equal to 1 plus 2, then c2 is equal to 3. Now just we finding the values of c1 and c2, which is substituting in our general solution, then we get the particular solution. Then particular solution is y of x equal to c1, that is 1 plus c2 x, then 3x e raised to minus 2x. This is our particular solution. This is all about the topics homogeneous linear differential equation of case 1 and case 2. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. In next upcoming lecture, we discuss about the homogeneous linear ordinary differential equations has case 3 and case 4. Thank you so much for watching me.